Hi everyone and welcome to a new video about noise analysis in op-amp circuits, and this is our example number 5. In this example we will look at an inverting amplifier with a feedback RC low pass filter. So we will also do the calculation step by step and we will verify these in SPICE simulation. So let's look at our example. We have the following circuit given, which is an inverting amplifier which has a feedback capacitor. The input resistance is R1, which is 1 kilo ohms, and we have the output, the feedback resistance, which is R2, is 5 kilo ohms, and the capacitor, which is in the feedback, has 3 values, and we will do that for 3 cases, so 1, 10, and 100 nanofarads. The op-amp here is OPA 209. Now we would like to calculate the input referred RMS noise voltage and also the output referred RMS noise voltage for these 3 cases. So let's look at our solution step by step and try to determine these 2 values for each value of the capacitor. So the solutions, before we move on in the more details, we will look at the op-amp specifications. Op-amp specifications that can be seen from the datasheet of the OPA 209 op-amp, and we have the plots here that will show you the response of your input noise voltage spectral density and also the input noise current spectral density. In addition, you have some parameters and some test conditions that will also be important to do the noise calculations later on. Now what you see here first of all is the open loop voltage gain, or the DC open loop voltage gain, which has a value of 132 dBs. It's also shown here in the table. What you also have is the gain bandwidth product, which is a very important parameter in the noise analysis. It has a value of 18 megahertz for this op-amp, and it's also shown here in the table. Now specifically for noise analysis, broadband noise voltage density E sub n BB, so the small letter E sub n BB, it is 2.20 nanovolts per root hertz, and that is shown here with this unit, and it is defined. The test condition is 1 kilohertz, so it is at 1 kilohertz and up to higher frequencies. You can also see that from the graph here on the left side. You can see this part is frequency independent, so it is not changing as a frequency, and has a value of 2.2 nanovolts per root hertz. And this region is a different region, which is called the frequency dependent region, or the 1/f noise region. We will see that later on. Now in a similar form you will have it also for the broadband noise current density, but given by this symbol. It has a value of 500 femtoamps per root hertz, and that is shown here in this table, also defined in the test condition of 1 kilohertz. And that is also seen in this plot on the right side. For the current, you can see it is 0.5 picoamps per root hertz. That's of course equal to 500 femtoamps per root hertz. Now let's also look at these 2 regions, because the input noise current spectral density has also that frequency dependent part. Now first for the noise voltage, we have the 1/over noise voltage spectral density, and it will be defined now in this case at 0.1 hertz, given by this symbol. It has a value of 20 nanovolts per root hertz. That is shown here. So 0.1 hertz, it is 20, and we will use this value later on to also determine what the effects of this small region. The 1/f noise current density, again defined at 0.1 hertz, is given by this symbol. It has a value of 3.75 picoamps per root hertz. It's shown here, again at the same frequency. Again, look at it, because this is a log scale. This part seems to be large or comparable to the broadband noise part, but this is only approximately maybe 50 or 40 hertz long here, and it is also here approximately maybe 200 or 500 hertz long, but this is actually much longer because it is in log scale. It might seem it is same in distance for the frequency, but it is much smaller, so the contribution for the 1/f noise will be later on seen that is actually not that significant for this case. So let's look at the circuit performance now in more detail, because that will be of course used and will determine our noise performance of the circuit also. Let's first determine the gains and I purposely used the gains instead of gain because you have the signal gain and also the noise gain. The signal gain will be of course used to determine the signal at the output, so that is the gain used to amplify the output. And you have the noise gain, which is then the part to amplify the noise at the input and the output. So the signal gain now, just looking in DC condition, which is then 0 Hertz, the capacitor will be then open, you have then a very familiar formula for the inverting amplifier, which is the minus R2 over R1. Now if you do calculate now that using the 5000 and 1000 ohms, you will have minus 5 for the signal gain. And this is the gain that will amplify your signal in DC. For example, if you have 1 volts DC here, that will be 1 millivolts, I mean DC here, that will be minus 5 millivolts DC at the output. Now, if you have also the noise gain, because that is important, want to calculate that, that is defined actually as the noise source located at the non-inverting input of your op-amp. Again, considering the DC condition, which is the capacitor will be an open or 0 Hertz, then you have, looking at this from this node, that this circuit is a non-inverting amplifier. Again, this is a short because it is disabled for noise analysis, the signal source. So you have then 1 plus R2 over R1, and you have the 1 plus 5000 over 1000 will be a 6. So you can see the noise gain is different than the signal gain. So in the absolute sense, the signal gain is just 5, but noise gain is larger, so you have 6. So in most cases, it is different, but in some cases, it can be of course the same, but you need to use the noise gain to calculate your noise performance of the circuit. And the signal gain is just given here to emphasize that it is different than the noise gain. It's not always the case, so make sure that you use the noise gain correctly. Now we have also the noise and the signal bandwidth. So signal bandwidth is of course given by a different formula, and the noise bandwidth will be given by a different formula. So you have the signal bandwidth and then you have the noise bandwidth. So the signal bandwidth is calculated using this expression, where we need the gain bandwidth product of our op-amp and also the noise gain. So the gain bandwidth of our op-amp was 18 MHz from the datasheet of the OPA209, and the noise gain for this circuit specifically, we have seen that it is 6. So if you now calculate this, you will have 3 MHz. The important thing is here is the signal bandwidth here is calculated using the gain bandwidth product and the noise gain of the circuit. But we have, of course, not only one op-amp, we have also another part which will also determine the frequency. So we have, of course, one op-amp, but we have also the RC low-pass filter in feedback. Now, we need to now be very careful what the value is of that capacitor and also what the effect is for the frequency response. Now, the pole frequency for this part, which is now given as P1, associated with this low-pass filter, R2 and C, is given by this expression, which is very similar, very familiar expression. Given in omegas, it was 1 over RC, very standard form, but it is now in hertz, so P1 is 1 over 2 pi R2C, and C will change, and R2 will of course be always 5000 ohms. If I now look at the 3 cases for the capacitor, so first for 1 nanofarads, the value will be for the P1 31.83 kilohertz. Now for the capacitor of 10 nanofarads, it will be then 3.183 kilohertz, so it's actually 10 times larger for 10 times increase of your capacitor. If you now go to 100 nanofarads, the P1 will be 318.3 hertz, or it is 0.3183 kilohertz. So you can see in table, in the feedback capacitor, if this increases, the pole frequency will decrease, but these are the values for each capacitor. Why is it important to calculate first? Because if the pole frequency P2, which is a different pole frequency, caused by the gain bandwidth product and also the noise gain, which is given actually by this expression, just to name that as a different pole frequency, is 3 kilohertz, but our pole frequency due to that feedback capacitor and the feedback resistor is different, and you need to make comparison between these two. So if P1 is lower than P2, then the actual signal bandwidth will be limited by the pole frequency P1. You might ask, what is lower? Is this 2 times lower, 10 times lower, 5 times lower? It is of course just a rule of thumb for several applications, but it is most of the time taking as a decade lower than the P1 or the P2 will dominate. So if you look at these cases, the pole frequency P1 is always much smaller than P2 for all capacitor values. For example, the smallest capacitor value will of course produce the largest pole frequency. It is, let's say, 32 kilohertz, rounding off this. It is still much smaller than the 3 megahertz. So it is 3000 kilohertz, and this is approximately 32 kilohertz. So it is approximately 100 times smaller than that one. It is at least 1 decade for sure. And that is of course for this one for sure the case, and this also for the sure the case. So you have actually for all capacitor values, for all cases, the P1 is much smaller than P2. Then the signal bandwidth will be limited by the P1. So the closed loop signal bandwidth then is determined by the feedback RC low pass filter in this circuit. Now, of course, the complete circuit will be a second order because we have the second pole due to that op-amp, and the first order due to that feedback RC low pass filter. But for the noise analysis, the first part of the frequency response, where we actually have the significant contribution, that is actually a first order response. So we can then assume that this is a first order circuit or a first order system. Now for a first order system, we use the Brigwall conversion factor, which is given by the value of pi over 2 as a symbol K sub n. This is for the first order. If you have a second order, you will have a different value. If you have a third order, you will also have a different value, but the details I'm not going to discuss here. Now the closed loop signal bandwidth, I mean the noise bandwidth, is very important now because that will be used for our noise calculations. So the noise bandwidth is calculated in the previous examples in cases where we don't have the external capacitor or any other components which will determine the frequency response. That was the conversion factor times the signal bandwidth. Now the signal bandwidth is limited, so it is not 3 megahertz here, it is actually the P1 associated with each capacitor. So we will have K sub n times the P1 for the noise bandwidth. So if you now do that for each case, you will have actually this value. So 50 kilohertz for 1 nanofarad, for 10 nanofarad it will be 5 kilohertz, and for 100 nanofarad it will be 500 hertz. So you can see the noise bandwidth will decrease for each increase in the feedback capacitor. So also the total noise voltage. We have of course the input referred RMS noise voltage and also the output referred RMS noise voltage. Now these two are related by the noise gain given by this expression. So the output is noise gain times the input noise voltage. But the input referred RMS noise voltage is composed of 3 parts that can be seen in more detail using this model of the op-amp. So the op-amp here has a noise, but this model has now this triangle is noiseless, and it has now added 2 noise sources, which is the noise current source here given by this symbol and noise voltage source at the input for this op-amp. Now this will contribute noise at the input, noise voltage. This will contribute noise voltage at the input, and we have also the resistors that will also cause some noise voltage at the input. So all of them, the first one is of course due to that internal op-amp noise voltage source. The other one is internal op-amp noise current source, so actually this will then also cause some input referred RMS noise voltage, and it's also the thermal noise voltages due to that resistors R1 and R2. So you have actually 3 values that will be of course determine the actual input referred RMS noise voltage. Now you can calculate the input referred RMS noise voltage using root sum of squares by using these 3 elements in this expression. You can see it is a root sum of squares because you square each term, add them up, and then take the square root. That will give you the effective input referred RMS noise voltage. Now, let's also then look at each part. So the input referred RMS noise voltage due to the internal op-amp noise voltage source. So due to this only, so all of them will be disabled, just looking at this part. Now that is on its own is also composed of two parts, because we have seen the plot of the noise current and the noise voltage. It has the 1/f noise part, which is frequency dependent, and it also has the broadband noise part. So the broadband and also the 1/f noise part. That will be of course used, these two, again using root sum of squares, to calculate the input referred RMS noise voltage due to that op-amp noise voltage source, using this expression. So let's look at the broadband noise voltage first. That is given by this in RMS. So the broadband noise voltage in RMS is given by the input noise voltage spectral density times the square root of the noise bandwidth. Now looking at the op-amp datasheet in the specifications, we have seen that the broadband noise voltage density was 2.20 nanovolts per root hertz. So that will be used in here, and the noise bandwidth will be of course determined by our feedback capacitor, and so also the R2 as the pole frequency P1. Okay, the 1/f noise voltage is given by this expression, which is then a normalized noise voltage for the 1/f noise part. We have the upper frequency and the lower frequency. So this upper frequency or upper cutoff frequency is also defined as closed loop noise bandwidth. So we will just substitute the noise bandwidth in here. The F sub L is the selected frequency to calculate your 1/f noise voltage shown here. And for that we will use a datasheet. You can see this value will be calculated at some frequency, and it is most of the time taking at 0.1 hertz, but any other value will do. And if you look at the specifications for 1/f noise voltage spectral density at 0.1 hertz, you can see it is 20 nanovolts per root hertz. So that's actually for the case when you have at 0.1 hertz. Now the normalized noise voltage then is given by this expression, just using the value from the datasheet and then times the square root of the 0.1 hertz, and that will give you 6.325 nanovolts RMS. Now, if I now summarize the values for each value of the capacitor, also for the noise bandwidth, we will have this value. We have seen this. Now we will calculate the broadband noise voltage for each case using this formula. You have this value. Now the values for the 1/f noise voltage will be of course calculated using this. Substitute in here this 6.325 nanovolts RMS. In here the noise bandwidth for each capacitor, and you have 0.1 hertz here, and you will have these values. Now to calculate of course what we require in this step, you will take the square of this one plus the square of that one, and then the square root of the sum of them, and you will have these values. What you see here in this table, in this column, is this value is very close to the broadband noise voltage part. So this is very close to that one, this is also very close to that one, and this is also very close to that one. That means actually the broadband noise voltage is dominating in this case. So we have now the first part of our input referred RMS noise voltage. The second part is the input referred RMS noise voltage due to the internal op-amp noise current source, and given by E sub Ni. So it is then due to this one, and the rest of the sources will be disabled. Now it is calculated using the equivalent resistance, because the noise current will flow through these resistors, and the noise current will be also an RMS value, so that will be also determined. So this will be again converted to an RMS value. Now the equivalent resistance then is seen by the noise current source, which is then shown here. Then using Ohm's law, we can then calculate the value also in volts. So the input referred RMS noise voltage due to this source, input noise current source of the op-amp, will be then used times the resistance, and that will be your input referred RMS noise voltage. Now this I sub n is on its own also composed of two parts. We have also seen the plot for the noise current density. It has a broadband and also the 1/f noise part. So that will be also used, and the formula is again calculated using the value of that will be calculated using the root sum of squares. given by this expression. So we need to also do the broadband noise and also the 1/f noise part for this noise current. So very similar formula again. This one, we have the value here for the broadband noise current density for the op-amp. Also the noise bandwidth, and you will take the square root of that for each case for the capacitor. The 1/f noise current, very similar formula. Again, FH for the noise bandwidth, FL the specific frequency to also calculate the 1/f noise current. And we will take also in this case 0.1 Hertz, but any other value will do if you just also look only in the 1/f noise region. Now you can see we also calculate the normalized noise current, this value, using this formula. We can see this symbol here, it is defined as 0.1 Hertz. It has 3.75 picoamps per root Hertz. We have also seen that in the previous discussion. Now that times the square root of the 0.1 Hertz, you will have this value, and this is what we need to substitute in this expression. Now this will be the noise gain for the specific case for the capacitor, and this will be always 0.1 Hertz, since we have chosen this also in the specifications of the op-amp. Now, combining again the capacitor and for each capacitor noise bandwidth, we can now have the broadband noise current using this formula and the 1/f noise current and RMS for this using this formula. Now, taking these two, using the root sum of squares for the input RMS noise current, you will have this one, and again you can see this value is very close to, in this case it's exactly equal to the broadband noise current. So again, the broadband noise current is now dominating. We have actually already mentioned this during the discussion of the datasheet. The 1/f noise region for this op-amp is very small compared to the broadband region, so that's actually why we have a very small contribution here by the 1/f noise current, and also was it for the 1/f noise voltage. Now, of course, we want to have the value at the input as the input referred RMS noise voltage, not the noise current. So we need to do another additional steps. So the equivalent resistance seen by this source in RMS will be then calculated first, and that is the parallel combination of R1 and R2, because this source, by disabling of course your signal source, and also this will be a short, just looking at the noise current source, will be the R1 and R2, of course, because the noise current will not flow through the capacitor. So we have only R1 and R2 in parallel, considering the output node also as a ground. So that will be 1000 in parallel with the 5000 ohms R1 and R2 in parallel. That will give you 833 ohms. Now, using Ohm's law, that means actually for each value here, you just multiply that by 833. So it's actually this one, which is also shown here, just to repeat here for convenience. That will result in these values. And what we see in this table is when the capacitor value increases, the noise bandwidth will decrease because the pole frequency will also decrease. And for each case, the value will be decreasing because the broadband noise current will decrease, the 1/f noise current will decrease, input RMS noise current of course will decrease because it will depend on these two, and because it is linearly dependent here in the input RMS noise voltage, this will decrease also. So by making the capacitor larger, you will filter out more noise because the input will be smaller for the noise. Okay, that's for the second part. Now we will look at the third part, which is then considering only the R1 and R2, only of course using the white noise. So it will be calculated using white noise or the thermal noise formula for the resistors. In this case we have of course R1 and R2, and that is our parallel combination, which is seen by this node. Okay, the thermal noise RMS voltage for the resistors in general is given by this expression. Now we need to of course discuss what the parameters in here are. So the 4 is just a 4. The K is the Boltzmann's constant, so it is 1.38 times 10 to the power minus 23 joules per Kelvin. The T is the absolute temperature in kelvins, so at room temperature, let's say 27 degrees, which is a little bit hot. Then we get a round number for the T, which is 300 Kelvin. So that is actually what we most of the time use also in this example. The R is the equivalent resistance in ohms seen at the node. So for at this node, we will see R1 and R2 in parallel. Of course, we have also some resistance here, but that's of course short of the ground, so that's 0. That's why we don't take that into account. We also have a noise bandwidth, and that will be also used here. That will be given in hertz. So in our case, for this circuit, the R was the equivalent resistance. That was 833 ohms. Now, looking again to the capacitor values and also the associated noise bandwidth, if I use this formula with this resistor value, I have these values. Okay, that is what we have. The next one is the situation where we also need to calculate the input revert RMS noise voltage in total. Then that is calculated using root sum of squares of 3 parts, which is then the terminal noise voltage due to the resistors, the input noise current source of op-amp will also produce some input revert RMS noise voltage, and also the input revert RMS noise voltage due to that noise current noise voltage source of the op-amp. Now those of course will be calculated using the root sum of squares. We have now the green part, which is the terminal noise voltage due to the resistors. Now this was calculated already in the previous discussion. That was the input RMS noise voltage due to that current source of the op-amp, and we have the input RMS noise voltage due to that noise voltage source of the op-amp. Now these three we have now, and we will now use this formula to calculate the input revert RMS noise voltage. And you can see the values here. What you also see is this value 868, for example, nanovolts RMS for 1 nanofarad is closer to the terminal noise voltage due to that resistor. So that is dominating actually. You can also see it in the second case and then also in the third case. Now that's what we have now for the input revert RMS noise voltage. Having determined the input RMS noise voltage for each value of the capacitor, we can now calculate the total output revert RMS noise voltage. That is calculated using the closed loop noise gain. For this circuit we had the noise gain of 6. Now when we use the input revert RMS noise voltage and multiply it by the noise gain using this formula, we have then the output revert RMS noise voltage given by these values. So for each capacitor you have the noise bandwidth and you have also the input revert RMS noise voltage and also the output revert RMS noise voltage. Which you can see again, the noise at the input and also of course consequently at the output will decrease if you increase your capacitor, so you have more noise filtering. Okay, that is for now, and let's also look at the noise signal noise ratio SNR. Now briefly, signal noise ratio SNR is a measure that compares the desired signal level to noise level, and in a more precise way the definition is actually a ratio of signal power to noise power, often expressed in decibels. Now if you have a ratio which is higher than 1 or greater than 0 dBs in dBs, it indicates you have more signal than noise. But if you have a ratio which is between 0 and 1, then you have a value which is then in dBs negative, so less than 0 dB. That indicates you have more noise than signal. That's of course what we don't want. We want to have more signal to noise ratio, so we will have actually more signal than noise. Now for this circuit, the SNR at the output for a specific frequency, we will see that in more detail in this simulation results, can be calculated using this formula. And in this formula we will see the output revert RMS noise voltage. So for our case we had several values for the output revert RMS noise voltage, and that will be then substituted in this expression and we get directly also the value in dBs. So that is what we have here for the output signal to noise ratio SNR. What you see is the capacitor value will increase and the signal noise ratio will then also increase. So more filtering, more signal noise ratio. What you also see in the conclusion is here the following. The first observation is that SNR increases by 10 dB when the capacitor increases by a factor of 10. So for each decade increase in the capacitor value will increase your SNR by 10 dB. So it goes from 105, let's say, approximately, to 115 and then to 125 dBs for each decade increase in the capacitor value. Now, a larger capacitor will then increase your SNR because you filter out more noise. That's actually a very logical consequence of that one. Okay, that's for the signal to noise ratio. Now, before we move on to the simulation, it is also very important to discuss integration bandwidth, which is a term in this circuit very important. What is integration bandwidth? Before we look, of course, to our circuit in more detail, we need to also consider actually at high frequencies the capacitor in the feedback. Because at very high frequencies, the capacitor will be a short, or considered to be a short, and then you don't have actually a signal at the output, so your signal gain will be 0. But the thing is, since the noise source at the input is a non-inverting input of your op-amp, the noise gain is still present here, and it is in this case unity, so it is actually unity gain feedback. So that is actually a very important part, because at high frequencies you still have noise gain, so the noise voltage at the output will not be limited if you integrate the noise up to infinite frequencies. This is a very important point, because we most of the time assume that the noise will be filtered out and it will be just 0 for very high frequencies, but in this case it will integrate up to very high frequencies and it will just keep increasing without limit. So that's why we need to use the integration bandwidth. Now, that will be, of course, clarified in more detail later on. The total output noise voltage then increases without limit for all cases, actually, for this capacitor. It doesn't matter, it only depends on the frequency. So technically, of course, in theory, we always need to integrate to infinite frequencies. But we, of course, want to have the following discussion. The key point is that we need to integrate beyond the cutoff frequency, because we have that conversion factor by the brick wall conversion going from the signal gain to the noise gain. Now, of course, in noise simulations, we need to integrate beyond the cutoff frequency, or the -3 dB bandwidth, or the noise bandwidth. But if you integrate in SPICE up to very high frequencies, it is not any practical, and also not numerically correct, to integrate up to, for example, 1 tera or 10 terahertz. However, this is not necessary, because the contribution of noise spectral density at a decade, let's say 10 times larger than the cutoff frequency, is not significant anymore. So, looking in a practical sense, we will not integrate up to very high frequencies, but let's say a decade or so larger than the cutoff frequency. Now, during the integration, the total noise should converge, that's important, to a final value. And that will include then all the noise before and after the cutoff frequency. So we will see that in great detail when we do the calculations now. In summary, what we can say is the following. It must be stressed that the noise after the cutoff frequency limit needs to be included in the total noise. And as a rule of thumb, we engineers, we of course want to have a practical sense for this analysis. We usually integrate at least 1 decade after the cutoff frequency. So once you know your cutoff frequency, you integrate actually 1 decade after that frequency. So you determine your cutoff frequency and you do that 10 times, for example, at least 10 times, and that will be your value where you need to determine your noise. Now, using this rule of thumb, the frequency where we should determine the output noise voltage for each value of the feedback capacitor are as follows, and then using that is the integration bandwidth, and this will be called the integration bandwidth. So the integration bandwidth, IBW, for example the capacitor of 1 nanovarads, the value is 10 times the signal bandwidth. Now the signal bandwidth, because 10 is just 1 decade after the cutoff frequency, the signal bandwidth for the 1 nanofarad was this. So it will be just 10 times and you will actually look at this frequency to determine the noise. Now, the similar form for the other two values for the capacitor, you have your associated integration bandwidth. So these are the frequencies where we determine the noise at the output and not the frequency, for example, at 1 giga or 1 terahertz, which will be of course done in theory. Okay, now let's look at the simulation results and clarify this in more detail. And then first we start with bandwidth and also in general the frequency response. So this is the plot. This is our circuit. We have now three plots here, the blue one and the green one and the pink one. So the blue one is the case where we have the capacitor of 1 nanofarads, 10 nanofarads, and this is the 100 nanofarads. And it's the gain plot. You can see for each case the DC gain is approximately 14 dB, and 14 dB is then in the DC gain. If you do the math here, going from the dBs to scalar, it is then 5, and we had also 5 in absolute sense. It's 5 over 1, so that's our inverting amplifier gain. So that's correct. And we have also the cutoff frequencies for each capacitor value, and that was also calculated. Now the first one is the DC gain, that was correct. The second one is the cutoff frequency for capacitor 1 nanofarads, and then the 10 nanofarads, and also 100 nanofarads. You can see the calculations and the simulations do match exactly in this simulation results, so that's all fine. We also see something which is maybe unexpected. So this is just of course the first order behavior. So we have DC value, and then we have the cutoff, and the line will of course decrease with a slope of minus 20 dB per decade. But we have at, let's say, around 1 megahertz, and this is a little bit larger, but for the pink one is 1 megahertz and the other one is a little larger, but it starts to increase due to some zero in the system, which is of course the effect of the op-amp and all the components around it. So it is actually a second order effect which we haven't discussed, and we haven't seen this in our model. And then it will approach a constant value. But the thing is, the noise analysis was actually up to say 300 or 400 kilohertz in our case. So it will actually stop around here, and we don't actually bother much about this part. So that will be of course not really interesting in our case. But if your integration bandwidth or your noise bandwidth is much larger, then this part must be considered, and it is of course a different topic, and it will be not discussed in this example. So we don't have to worry about it. Now let's also look at the input noise voltage spectral density. Again, we see the input noise voltage spectral density for each case for the capacitor. So the blue one, the green one, and this is actually the pink one. So this is actually the highest one. Now what you see here is the frequency dependent part, 1 over f noise, very is this part. But you have also see the independent part, which is then the broadband part, but you have also that peaking, which is unexpected, and it's actually at this part. And we have also seen that in the plot, in the body plot, that at this frequency around 1 megahertz and a little bit higher for others, that there was some unexpected increase in the body diagram for the gain. And that's actually the 0, and this is actually that unexpected part. But that is actually not what we are interested in, so we can ignore that for our circuit. Now we also look at the output noise voltage spectral density. That's for this one, the blue and the green and the pink one. For each capacitor value, you can see it starts like a 1 over f noise region, has a broadband noise part, and it will then approach again 0 due to that filtering. That is actually what we have for the op-amp noise, or output noise spectral density. So again, independent part, the dependent part is the 1 over f noise, independent part is the broadband noise, and also the output goes to 0 due to the band limit of the RC circuit. Okay, now let's also look at the total RMS noise voltage, which is now very important, and that's actually what we have discussed as the integration bandwidth. You can see the blue, the green, and the pink one. Again, the blue one is the case where you have the capacitor 1 nanofarads. The green one was for the 10 nanofarads, and you have the pink one, which is for the 100 nanofarads. Now what you see here for the capacitor, here you have the total output RMS noise voltage. The calculated value was 5.81 microvolts RMS. And we have now simulated this because if you look at the graph, it will just keep increasing. That's actually what we have discussed as the shorting out this capacitor for very high frequencies will cause, of course, the noise still increase at the output because the noise gain is 1. It's not filtered out. So it is, in this case, not 0. So we have then defined or discussed the integration bandwidth. So looking at the integration bandwidth, in our case it is at 1 decade after the cutoff frequency for this case, so it is 31.83 kilohertz, so 10 times that one will be then this 318.3 kilohertz, and that is then 5.71 microvolts RMS, and that is then very close to what we have calculated. Now if you do that also for 10 nanovolts, again at the integration bandwidth, it was calculated 1.84 microvolts, it is now 1.82 microvolts, so that's actually also a really nice result. Again, for 100 nanovolts, farads for the capacitor, you have this value which we have calculated, so it is 591 nanovolts RMS, but we have here 598 nanovolts RMS, so also very close to what we have calculated. So the simulation at the integration bandwidth and also the calculations do match very well. In this case, again, important, you need to look at the integration bandwidth to determine the actual value. So if you go all the way to, for example, 1 gigahertz, you will see that it will be 14 microvolts RMS, which will be, of course, not the actual value for the specific case. So again, integration bandwidth is important, and the rule of thumb is integration bandwidth is 10 times the signal bandwidth, and we have used this in this simulation. Okay, signal to noise ratio also very important. We have for 3 cases, the blue, green and the pink one. The blue one is for 1 nanofarads, the green one is for 10 nanofarads, and for the pink we have the for 100 nanofarads. Again, we have also determined that for the integration bandwidth. So for the blue one, this is the integration bandwidth, and we had 105 approximately dBs. Now we have now for the capacitors these values, output signal to noise ratio, and we have calculated these values in our discussion, and this is the simulation now, again looking at the integration bandwidth. What you see is really nice. This was 104.7 dBs and this is now 104.9 dBs. Now these are really close to each other. This is also very close to each other, and this is also very close to each other. So we can see the simulation and the integration bandwidth for SNR do match very well with our calculations. So that's actually also a really nice confirmation that this is correct. And again, we have used the integration bandwidth here as a rule of thumb. Integration bandwidth is the 10 times the signal bandwidth, and that is where we have determined our SNR. Alright, this is actually for this example where we have seen in more detail what the effects of our feedback capacitor and also the feedback resistor, that this will dominate for specific values the frequency response of our circuit. In addition, we have seen that the integration bandwidth comes into play because the capacitor and the feedback will be a short for very high frequencies, and the noise gain will be unity, and that will cause, of course, the output noise keep increasing where we have, of course, no limit anymore. So the integration will go on and will have, of course, no limit, and that's actually why we need to use, in a practical sense, as an engineer, the integration bandwidth to calculate the actual value of our noise at the output. Alright, this was for this example, very detailed example about that noise analysis of an integrated circuit. And of course we will do that for different circuit also. So if you have any questions about this, please let me know and I will try to answer them as soon as possible. Thanks again and see you next